Hello everyone, welcome to Statistical Methods. In this video we'll be talking about entropy and about Kullback-Leibler divergence. If you'd like to study this yourself, then look at the lecture notes into the section 2.1 and 2.2. So let's get started. So in this video we'll be talking about essential concepts from information theory, because those concepts underlie all the statistical methods we will be discussing in this course. So entropy forms the foundation both for likelihood inference as well as for Bayesian inference. So let's just give you a brief overview about entropy, because there is some confusion about the different types of entropy, and some of them are from physics, some of them are from computer science. So let's talk about the Shannon entropy and the relative entropy, and those are the two types of entropy we'll be focusing on. So we have what we commonly call entropy in information theory goes back to those two types of entropy. So we, on the one hand, we have Shannon entropy, and this Shannon entropy was invented by Claude Shannon, and published in 1948, but all of these entropy stuff was actually invented during World War II, and then it was classified because it was used for cryptography. And then we have relative entropy. So this is Shannon entropy, of course, by Shannon. And then we have relative entropy, which is due to Kullback and Leibler. So these were also cryptographers, and they published their paper in 1951. And so this is called relative entropy, and we'll come to the precise definitions in a few minutes. So these are classical entropy measures, and of course actually the term entropy goes back to a physicist called Ludwig Boltzmann. So he is an Austrian physicist, and he actually invented entropy, if you can say invented entropy, around 1875, when he was studying thermodynamics. So he was the founder of statistical physics, how it's called, and he was studying thermodynamics. So basically he looked into gases and systems of particles, and to characterize the states of those systems he used entropy, and it turns out that mathematically the entropy he discovered is exactly the same as actually the relative entropy by Kullback-Leibler. So some people call the Kullback-Leibler divergence actually the Boltzmann-Kullback-Leibler divergence, even though they were invented in different contexts. So these are the basically founding fathers of entropy. And interestingly, so you can see that these were like mid-20th century, and of course this is the result of a lot of other research, and encompasses other things like likelihood or Bayes, as we will see. So there are, just to give you a few other names, so entropy has been and it still is a current field of research, and there have been a lot of people working on this, and some famous names you may or may not encounter. One is Edward Janes. He has a very, very good book on probability theory, Janes. Then we have Good, who was British and actually briefly also working at Manchester University. Hartley, also British. And Turing, of course, also working at Manchester. And they also made contributions to the study of entropy in computer science and statistics and information theory. So let's start with, before we go to entropy, let's start with some definitions. So we first look into a discrete random variable. And we'll come back later to the case of continuous random variables, but for the moment we have a discrete random variable. And this random variable x has a state space omega, and you have it can take states x1, x2, k. So we have k options, and k is finite, and we have a associated distribution f. Distribution f, and of course we have a probability mass function, which is f xi would be the probability that x equals xi, and that I call pi. So the sum of the probabilities pi add up to 1. So that's our discrete random variable. And so now we can define something that's called the surprise. So these pi, so every pi is in the interval between 0 and 1, because this is our probability. So now the surprise is defined as minus log p. So the surprise, so if we have an event with 0 probability has a, or let's say pi is 1, then the surprise is 0. That means when we have a certain event with probability 1, then we have no surprise. And if pi is 0, then, so if we have a event that actually doesn't take place, then the surprise is actually infinite if it actually takes place. So that's the different scale. So basically the surprise is just a different scale how you describe probabilities. So it's a transformation of a probability. So minus log the probability is called the surprise. And now what Shannon did, Shannon defined his entropy. Entropy is expected surprise. So that's his idea. And formally, entropy has the Shannon entropy is denoted by an H, and if it's basically a quantity that summarizes a distribution. So it's a function of a distribution, and that's the expectation with regard to the distribution, of course, of minus log the probability function. So, and of course, because we have so that's the general definition. So because we have discrete probabilities, this is simply the sum over all possible states, pi log pi. So that's the Shannon entropy. So far so good. So how can we interpret this? So let's have an example. Example 1, that we have a uniform distribution. So uniform, by uniform I mean that the pi is 1 over k. So all the probabilities of the individual events have the same probability. And then it's clear that the Shannon entropy becomes log k. So that's one example. So that's just the entropy when for the uniform. And the example 2. So let's say this is example 1. Example 2. We say we have distribution that looks like this. So this is our probability mass. So we have 0, 0, 0, 0, and then one peak, and then 0, 0, 0. So these are all our possible events. And here we have 1, or the 1 is here. So where's the see if I can move it. Oh yeah, okay. So this is basically concentrated probability mass. So basically the opposite of uniform. And then it turns out that the entropy is 0. So, and that's the general pattern. So the entropy is maximized, and you find the details actually in the script. So entropy is maximal if it's uniform, and it's minimized when there is concentrated probability. So that's the idea, and that's what Shannon entropy actually characterizes. So this is the minimum, and that's the maximum. And it turns out that for discrete random variables, the entropy cannot be smaller than 0. So for discrete random variable, we always the entropy of any function is either 0 or larger than 0, and it's also maximized if it's uniform. So if something has maximum entropy, it means it's maximally uniform. So maximum entropy means maximally uniform, or in a way maximally uninformative. And that's where how entropy is often used to create distributions or find distributions that are maximally uninformative. And in the next step you could actually add some constraint, so you can have, you want a maximally uninformative distribution, uninformative given some other constraints, uninformative. So that's Shannon entropy. And if we apply this to uniform distribution, so not unit, to continuous random variables, so above definition for continuous random variables, then we end up something called differential entropy. So this differential entropy is basically Shannon entropy for continuous random variables. So it's defined as the integral over fx, if f of x is of course a density, log fx dx. And interestingly, this can be smaller than 0, can be negative, and the reason is that the density can be larger than 1, of course, so then minus log something larger than 1 is negative. So for the normal distribution, so we can compute this for the normal distribution. Turns out that the entropy of the normal distribution is ½ log 2 pi sigma squared plus 1. And I was saying, so maximally uninformative if this is large, and you can see it's directly depends on the variance. It doesn't depend on the mean. And so the larger the variance, the more uninformative distribution becomes. And of course, if the variance is infinite, then it's maximally uninformative. So that's the differential entropy. And as I said before, you can use this now to characterize distributions. And the uniform distribution is the maximum entropy distribution. And the for continuous variables, you can say, for instance, you want you specify the mean and you specify the variance, and then you can show, for instance, that the normal distribution is the maximum entropy distribution given a certain mean and a certain variance. So this is one thing why or how entropy is used. So now let's move on to something called the cross entropy. So if you have noticed so far, in the surprise, we have taken the expectation over a density or probability mass function, and that was the same density. Now if we can basically define the cross entropy by using different distributions for the expectation and for the density that we are taking the expectation of. So we can define the cross entropy between two distributions, f and g, as the minus the expectation with regard to f, and then we take the log density of the second distribution. So that's cross entropy, where f is the first distribution is the distribution that is assumed to be the true distribution, and g is supposed to be some sort of a candidate distribution. So it's not symmetric because they have different functions here. And of course we have, if we use the same distribution, then this becomes just the normal entropy. And it's bounded below. So it's easy to show that the cross entropy Fg is always larger, or at least at the same size. If f and g are the same, it's always bigger than the entropy of f. So the details, you'll find more details about this on the script, but you get the idea. So the idea is we just compute the surprise, but we use two different distributions here. So we can, as an example, you find an example about the normal distribution. I'll briefly write it down so that you see how it looks like. So let's assume we have two distributions, f ref, so that the first one is always the reference distribution. And let's assume this is a normal distribution with a mean, a reference mean, and a reference variance. And then we have our distribution f, which is just normal with mu and sigma squared. Then you can compute the cross entropy between f reference and f is 1/2 then you have several terms here, so you have mu minus mu ref, so you have a squared distance difference plus the ratio of the reference variance divided by the variance plus log 2 pi sigma squared. So that's just the cross entropy. And for instance, you see that some of these terms vanish when the means are the same or when the variances are the same. And if the variance and the mean are the same, then you can see that this becomes, of course, the entropy that we have seen here. So now, with this in place, we come to the most important quantity that we discuss in this video, namely the Kullback-Leibler divergence, or relative entropy. And the Kullback-Leibler divergence is simply defined as follows. So Kullback-Leibler divergence, or relative entropy. So what we have seen in the cross entropy, we've seen we have a quantity that allows us to compute the surprise of a model given a reference distribution. And we've seen that, or I've told you that the cross entropy is always larger than the entropy. And now the idea is, can we combine those two to get a quantity that has some really nice properties? And in particular, we like to have a measure that allows us to compare distributions directly. And the idea is now to define the Kullback-Leibler divergence that is written dKL, so divergence and Kullback-Leibler, and we simply take the cross entropy HF G minus the entropy, and then we have a quantity that can also be written like this. So if we plug in the definitions, we get, this is the expectation of the ratio of the log of the ratio of fx over gx. So this is the Kullback-Leibler divergence, and this has some really nice properties, and this is a quantity that is at the center of statistical inference actually. So this is a really important quantity that you absolutely need to memorize. So what it does, so basically this measures the amount of information that is lost if f is approximated by g. So, and if f and g are the same, then the divergence is 0. So if and only if f equals g, then the Kullback-Leibler divergence is 0. So I'll just give you a few properties, and in the worksheet you'll prove this yourself. So so we can use this to figure out whether two distributions are the same, and otherwise dKL is a measure of the information lost when G is approximated by F. No, the other way around. Now when F is approximated by G. So F is the reference distribution. So F is the reference, and you can remember this because we have the expectation with regard to F. F is the reference. So there are two typical applications, as we will see later in the other videos. So F is the underlying data generating process, underlying true data generating process. So this is statistical applications, and G is our model of a family with parameter theta, say, and then we'll try to use the Kullback-Leibler divergence to find the optimal parameter theta. And the other application would be that F That's in Bayesian statistics, so I'll just mention it now. We'll come to that later. F would be a posterior distribution. And G is the prior distribution. And the update from G to F is also mediated by the Kullback-Leibler divergence. So I'll give you very few examples, and then I recommend that you study the examples in the worksheet, and you can find the solutions there as well. So the Kullback-Leibler divergence between two normals. So continuing the example from above, we have f ref and we have f. So, and then the Kullback-Leibler divergence between those two is simply the cross entropy between f ref and f minus the entropy of the reference distribution. And that is the following. So it's something that's very often used actually. So it's the mu minus mu ref squared divided by sigma squared plus sigma squared ref. So it's all in the script. So if you can't read it, then check it in the script. Sigma squared ref divided by sigma squared minus 1. So that's the relative entropy between those two. And you can easily see now if mu equals mu ref, then this becomes 0. And then we have if sigma squared equals sigma squared ref, and this becomes 1, cancels out with this one, and this is also 1, and log 1 is 1. So if then dkl is 0, of course. So you can see this directly, and otherwise it's positive. So that's of course also by construction, because we have seen that the cross entropy is bounded below by the entropy, and then if we subtract it, the difference is of course always positive. So dkl is always positive and larger than 0. So that's for the normal distribution. And then there are some other interesting things that we also look at in the example sheet is when we have discrete distributions. So let's say relative entropy between two discrete distributions. So we have probabilities P1, Pk, and then we have Q1, Qk. Then the Kullback-Leibler divergence between P and Q is Pi log Pi Qi, and what you'll show in the worksheet is that this, if you approximate this, so this is the exact form. So if this is approximated, and we do a Taylor series, and you do this in the worksheet, Taylor series, then we get into the Pearson or the chi-squared statistic. So from year one, you know that there are some formulas to characterize the difference between two discrete distributions, and one of them would be is sigma, not sigma, sum over the pi minus qi squared divided by qi, and this is the Pearson statistic. So there's actually a Pearson statistic and a Pearson divergence, but they are basically almost the same apart from a standardization. And then if we compute the same thing by divide by pi, then we have related statistics, and both of these statistics, so you can either divide by q or by pi, and both of them are approximations to the Kullback-Leibler divergence between two discrete distributions. And so every time you use this chi-square statistic or Pearson statistics, then you actually use Kullback-Leibler divergence. So so we stop here with this video. So to summary, there are quantities to characterize distributions. One is Shannon entropy or differential entropy, which is the expected surprise. And the higher this is, the more uniform the distribution is. Then we have the cross entropy, and from the cross entropy and the Shannon entropy we compute the relative entropy. And the relative entropy characterizes the similarity of distributions. So similarity of distributions, and this is the interesting bit for us in statistics, because in statistics we always like to find models that are allow us to interpret what's in the data. So what we will be doing, we will use Kullback-Leibler to compare the empirical distribution, for instance, with the model distribution, and then choose accordingly. But this is the subject of another video. That's it for today, so I hope you understood most of it, and if not, then please, because this is really important, please read the corresponding sections in the lecture notes and study the worksheet of the first worksheet, where you find a lot of examples. Okay, that's it for today, and then see you in the next video. Bye bye.